Hello, guys. I hope you're fine with the conference. Actually, this presentation is something Yuval Boger asked me to do. And I said, well, OK, why not? So it was about kind of trying to assess the roadmaps from different vendors in the FTQC realm and get an idea of what's credible or not. So I won't do some finger pointing on whoever is in the industry, but I will give you some insights on how you can evaluate and particularly how you can look at the challenges that all those vendors have to create those large systems with many logical qubits. The first thing you got to look at is the customer need. The customer need is to develop and run some algorithms. And I will use two charts which I've been using for a while, at least for the first one, which is resource estimates being done by the DARPA as part of the Quantum Benchmark Initiative program that was started about 2 years ago. And some benchmarks, and particularly resource estimates, were done by companies like Zapata and Rigetti. And they published very interesting papers a year ago. I think it was during spring and summer 24. And they provided some estimates. So when you look at these charts, what do you see? You see that for useful algorithms, typically in materials and chemical simulations, you will need a lot of gates. So it's estimated either in a Toffoli gate number or C0 or whatever. So it's basically the size of your circuit that's important. And you see that you're going to have a lot of gates. And it gives you an idea about the fidelity you need to create with your logical qubits. And then at the bottom, you see the number of logical qubits. And what's weird is when you look at useful applications like amyloid beta binding, it looks weird. It's something that could help understand Alzheimer's disease, for example. Corrosion, you understand. Developing new fertilizer or method to produce more efficiently fertilizer. These are all the chemical simulations that's important for many industries. And Shore is in between because, OK, people care about that, even though the usefulness is kind of questionable. And interestingly, when you look at the roadmaps of most of the vendors, what they plan is to reach a threshold of about 100 logical qubits by potentially the end of the decade. And when you look at that, you see it's below the needs of those algorithms. So one of the questions we're going to have is, what we will do at the beginning when we have the first 100 logical qubit systems? And what may happen is we will have a kind of mix of existing NISQ algorithms, using variational algorithms running on those systems. And it's going to be very challenging because the deeper those algorithms are, many problems arise which are not linked to the fidelities of the qubits, typically barren plateaus, problems with machine learning or whatever, VQE for chemical simulations. And then later, we're going to have so-called early FTQC, where you have real algorithms based on typically QPE for chemical simulations being used on larger systems. So now, recently, I think it was last week or 2 weeks ago, the DOE published a similar kind of resource estimate stuff, but only based on physics, quantum physics simulation, high energy particle physics, chemical simulation, and material simulation. And they landed up in kind of similar results, but in more fuzzy ways. So you see in that chart the needs, and I forgot what's in X and Y, but I think this gives you an idea of what we could do with the first FTQC systems. And it shows that some applications will be feasible on those systems, on those three categories. So it's always quantum physics simulation. Now, if you look at the landscape today, we have an amazingly large number of companies who are trying to reach that level. I think my last count is about 95 different industry vendors. Of course, you have large ones like IBM and Google and well-funded startups like PsyQuantum, IQM, Alice and Bob, Candela, not to forget my friend's fellow in France. And all those people try to reach the same thing. So they want to develop scalable systems. So now, if you look at the past is always a good teacher. When I started working in the quantum domain about 7 years ago, I remember Rigetti was promising that they would have a 128 qubit system 7 years ago. And right now, what they do have, they have an 84 system called Anka, and they've got a better one which has only 36 qubits. And IonQ is about the same. They were promising that in 2019 they would have about 79 computing qubits on top of 160 so-called memory qubits. And right now they have about 36. So you see that it's a challenge. I mean, and these are not long-term promises. These are the promises they were making for the year, the current year. So it shows that you have to be very careful when you look at the roadmaps. So now, if I take the eye of the end user, of course, what I need is to be able to run my software, my algorithm. So what I need is the support of a given number of gates and a given number of qubits. So the best roadmaps are those who provide 3 numbers. The number of logical qubits, but not just that, a number of logical qubits connected to a fidelity, which can be evaluated with a number of gates, because the fidelity is kind of the inverse of gates, or the error rate is the inverse of the gates. And because you want to know about the physical aspect of your system, you need to know also the number of physical qubits you need to achieve that. Because a number of physical qubits will give you an idea of what you can do with variable number of logical qubits and variable fidelities. Because you have more qubits and less gates, or more gates and less qubits. So there's some flexibility in those systems. But it's not enough. I mean, if I am an user, I want to know more. I want to know what is the clock speed of system, because it's going to condition the speed of the algorithm. I want to know what kind of error correction is going to be implemented, because it gives you an idea of how is it complicated to implement. And you'll see later that it's going to influence on the viability of the system. You want to know also about the size and a lot of practical elements, which I put in blue here, which has operational metrics, because I want to install the system in a data center, if I'm an HPC center, like all those members from the HPC JU in Europe or the DOE in the US. And if I'm using the systems in the cloud, it's going to be a problem for the hyperscaler, like what Julia was talking before, Amazon and others. But you need to know about the weight, the size, and some small detail, which is what's going to be the price of the system, because the price is going to be an important factor about how you scale the usage. And the last one is also the energetics, and I will talk about that later tomorrow in a different talk. So these are very operational metrics, which right now are missing. I've never seen any vendor talking about this. And as an end user, I would love to have that, particularly if I was running my own data center. So now if you look at the roadmaps that have been published so far, I assembled in this weird side the various numbers with the 3 colors. So the color for logical qubit, physical qubit, and the number of gates. And what you see is twofold. What you see is not all the vendors publish those 3 numbers, so which means many roadmaps are not complete for that respect. Some numbers are well crafted, like what you see with Alice and Bob, IBM. I forgot because I don't see anything in the screen over there. So, and I don't want to look backwards. So, and some companies provide only 1 number, 2 number. It's kind of wishy-washy. It doesn't give you a good idea. Then you have some companies who are very optimistic, like IonQ, since they acquired Oxford Ionics last June, or OQC in the UK. They are just promising in a couple of years to have tens of thousands of logical qubits, which may be challenging, to say the least. So now what I'm going to do is going to show what are the challenges for those companies. And they have multiple challenges. Some of them you know them, and some of them you don't hear much about it. The one you know well is the quality and quantity of the qubits. We all know that we need both to do FTQC. You need both, because if you have only quantity and no quality, you won't scale. And if you have only a good quality qubit, but you have only 2 of them, it doesn't scale very well as well. So you need both. And if you look at this chart, which I've been updating since 2023, you see that the current state of the art is a mix of companies and products, particularly with superconducting qubits. They have an average fidelity which is between 99 and 99.5% for 2 qubit gates, which is the right threshold. But you have to also look at the readout fidelity, which is very important, particularly when you run quantum error correction. And well, when you see the zones, there's one zone in yellow which corresponds to the NISQ viability, and which has this strange triangle zone, because if you have more qubits, you need better fidelities for a deep circuit. And there's nobody right now. So the trick of the trade that's been used for about 2-3 years now, particularly with IBM and its quantum utility mantra, is to use not as good qubit fidelities with about 21, 27 up to 156 right now, physical qubit, but you use quantum error mitigation, which is a post-processing trick to improve the perceived quality of the qubits for the software. But what you need to create an FTQC system is much higher fidelities and numbers. So you need to be in the green arrow and at multiple scale above that. Some qubits need only a couple thousand qubits to do a 100 logical qubit, like with Alice and Bob. Others need more. And so the dependency on the error correction, the many-to-many connectivity, and all of that is going to change what you need to move up. But you need more physical qubit and better physical quality, and that's a huge challenge. The second challenge, which is connected to the first one, which is less known, is how do you iterate in manufacturing the chips? Because in all technologies, maybe besides cold atoms, you need a chip. You need a chip for trapped ions, you need a chip for superconducting qubits, a silicon qubit, photonic qubits, it's a chip. Everything is based on chips. And so the quality of your qubits is going to be very dependent on the quality of the manufacturing, the quality of materials deposition, the quality of the defects, sometimes the isotopic purity, like what you need in silicon qubit. So you need to improve, at least based on what we know on the state of the art, you need to improve the quality of manufacturing. And to understand if the roadmap is credible, you need to look at the cycle. How long does it take from designing a chip to manufacturing, characterizing, and testing in a full system? It takes time. And this time is variable across the modalities. It's much faster in superconducting qubits, although it takes a couple months. And particularly when you install the chip within your cryostar, you've got all the cabling and it takes time. It's longer for photonic qubits, and it's even longer for silicon qubit. It doesn't mean one is bad and the other is wrong. It means that it takes time. And what we don't know yet, and there's some lessons from history to learn about it, is how many times you iterate this cycle. So I can give you an example. When Google released the Sycamore in 2019, 6 years ago, they had 53 qubits. They planned to have 100 physical qubits by 21, 22. And it became Willow in 24. So it took longer than planned. Why? Many reasons for that, but one of the reasons is they had to iterate with more cycles in producing new chips, and at some point they developed their own manufacturing clean room, so they changed from university-grade clean room to their own. And so all of that takes time. It's about the same as the semiconductor industry. It takes time to create new processes. The third one is QEC and FTQC. When Willow was released last year, it was a big performance, but you have to remember that the performance was about just correcting a memory. It was not correcting gates. It was not about FTQC, and they published later many papers, mostly theoretical papers, but they have not yet, at least with regards to Google, published the whole stack. So what do you need? You need to correct errors for single qubit gate and 2 qubit gates. Then you need to do the so-called magic state distillation, so create a so-called T-gate or autofoley gate, and you need to teleport the gate to somewhere else in your chip. And this is a whole bunch of things to do, and it's very complicated. And there's an overhead, even though Craig Gindley at Google found a way to reduce the overhead to do that with a magic state cultivation. But it's not enough. You need to correct all other kinds of errors, which are non-poly errors. So you need to correct correlated errors, like the ones coming from cosmic rays. You need to correct leakage error, like with the cold atoms, when you lose them, so erasure and leakage errors. And on top of that, you need to detect the syndromes in real time. So there's a lot of electronics and classical software that's involved. And you need also to do so-called code switching, which is the capability to dynamically switch from one code to the other and assemble all these things. It's a lot of work, and it takes time. And on top of that, you need to assemble all the enabling technologies at the hardware level, which will make it possible. So higher qubit fidelities, numbers, calibration, which is going to be a big problem, because I saw that with some qubit modalities, the frequency of calibration is higher than the length of your algorithm. So, okay, maybe Houston, we have a problem. So we'll have to find a way to synchronize calibration and the length of the algorithm, the circuit you want to execute. And in the end, you need also to look at interconnection, because some QPUs will have a limited scale in number of physical qubits, and you need to interconnect them, and then you have additional problems, circuit partitioning, error rates with untangled states between different QPUs, and it's another stack of problems. And most of the vendors, I think, maybe besides maybe Oxford Ionics, they all plan to have this kind of technology being involved with either microwave or photonic interconnection. The fourth is how do you orchestrate your enabling technologies? And right now, all the vendors, they have some trade-offs. And these are, I would say, unsolved trade-offs. Typically, I've got 5 of them. I won't list them all because I don't have much time. So the trade-offs you have is you choose, for example, to have either room temperature electronics, which consumes a lot of power, or you put the electronics in the cryostat, in the case of silicon qubit or superconducting qubits. But if you do that, you generate heat within the cryostat, because the cryo-CMOS, for example, generate heat. Or you replace the cryo-CMOS by another technology called SFQ, designed by 2 companies in the world, Quamco in Israel and CQC in the US. But it's still an unproven technology. Another example is, are you improving the manufacturing process, which may be long and cost some money, to improve the physical quality of your qubits and the scaling, or do you invest in interconnection? Probably we need to do both, but there's some trade-off over there as well. And if you take cold atoms and trapped ions, if you have more ions and more atoms to control, you will need more powerful lasers. But the more powerful lasers are, the more phase noise you have. So you need to improve the quality of the lasers, otherwise you're going to have too much noise, and the noise will generate decoherence, and it's going to drive a lot of problems over there. The last challenge is about software. What I did show in the first slide was mostly algorithms talking about physical and chemical simulation, physics, materials, and chemical simulations. But the big bulk of the market potentially is optimizations, machine learning, PDEs, or partial differential equations. These are the problems for companies who need to use a quantum computer on a daily basis. Transportation, financial services, logistics, whoever. What happened? No, sorry, my screen is wrong, what I see here. So, and so you need to make sure that there's enough research being done to improve the portfolio of available algorithms which will solve problems beyond the scope of chemical and material simulation. And it's probably the biggest problems in this industry at the software level. And one of the reasons is the known quantum algorithms to solve optimization problems, they have only a quadratic or polynomial speedup. And this is not enough, as shown in this graph, where I show that, sorry, I've got to go backwards. When you see in this graph is when the quantum algorithm is faster than the classical one, is at a high time, like what I call TP, so T polynomial. And most of the estimates that have been produced recently, particularly the paper that I mentioned from Studenmeyer and Van Tal at the bottom, it's about a couple of centuries. So you need to wait a couple of centuries to have a quantum computer being faster than a classical system. I don't think it's a good idea to wait that long. In the case of exponential speedup, it may happen earlier. And that's why quantum chemistry, which in many situations could bring an exponential speedup, brings more hope in that space. So you need to work a lot. But there's a lot of stuff to invent. I mean, when we will have TQ system, we will have to invent a whole bunch of software engineering tools, nearly reinventing, not the wheel, but reinventing all the process to develop software, to deploy the software, particularly when they're mixed with HPCs. This is an entirely new, I would say, discipline to build, and we are very early on in the development of that discipline right now. And you have to not forget that the classical computing ecosystem is making progress, particularly with tensor networks. So the goalpost is moving. NVIDIA and other competitors like Cerebras are improving their own classical chipset on a, I would say, not a daily basis, but every year. And they are improving even both the energy, the computing capabilities of the systems. So we have to take care that quantum computing is competing with other legacy systems which are making progress. So, as a conclusion, how do you build a good dialogue between end users and vendors? Sometimes it can be surprising to see vendors. I remember Hyundai working with IonQ and others. They publish not benchmarks, but more resource estimates. They say, OK, we want to simulate that molecule, and it's going to cost a couple thousand logical qubits. What's the sense of that? There's a lot of sense. It's even better than working on NISQ, because the vendors are fed by people developing algorithms, and they have an idea of what's needed. So it gives them an idea of what they need. So they need to establish that dialogue with the end users. And on the other hand, the end users, they have to learn. They have to provide the use cases to those vendors. And it's a continuous dialogue that has to be established early on, because the better the vendors are informed about the user's needs, and the users are both real end users like a chemical company or transportation company, and intermediate users in the ecosystem like the hyperscaler or the OVH cloud, the Amazons and Microsoft and Google who host the systems, and customers who will host their systems on their own data centers. So this is the stuff that has to be done, and the good dialogue between those two parties will enable the development of these systems. And don't forget about the economics. The cost of the system is going to be very important. One last word, I'm late, sorry, is I was part of a team which produced a report at the Academy of Technology in France, and it's a report on FTQC, so exactly on the topic that I was discussing right now. It's available in French and in English with that code, so use your phone to get the URL to get this. And I see you tomorrow. And I will continue my presentation with looking at the energetics of the system, and you will be in for some surprise about it. And you can get the slides right away. No wait for the publication of the slides on the Q2B website. Thank you very much. I can talk with you outside. Bye-bye.